the edge of the observable universe. Most people imagine the universe has some kind of wall at its edge, a physical boundary where space just stops. It doesn't. The observable universe is a sphere roughly 46.5 billion light-years in radius in every direction from Earth, and its edge isn't a barrier, but a horizon, the farthest point from which light has had enough time to reach us in the 13.8 billion years since the Big Bang. Beyond that horizon, space almost certainly continues. We simply can't see it. The universe's expansion actually means this boundary is always retreating, pulling potential information away from us faster than it can arrive. Think of it like standing in the middle of an ocean in thick fog. The fog isn't a wall. It's just where your vision ends. Everything beyond it is real. It's just permanently out of reach. The cosmic microwave background. Just before you hit that observational horizon, you'd encounter something genuinely extraordinary: the oldest light in existence. The cosmic microwave background, or CMB, is the afterglow of the Big Bang itself, emitted roughly 380,000 years after the universe was born, when things finally cooled enough for atoms to form and light to travel freely for the first time. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who initially thought it was pigeon droppings interfering with their antenna, the CMB now sits at a temperature of just 2.725 Kelvin, barely above absolute zero, and it blankets the entire universe in every direction equally. The tiny fluctuations within it, variations of just 1 part in 100,000, are the fingerprints of the earliest density differences in the universe, and every galaxy, every star, every planet that has ever existed grew from those microscopic wrinkles. It is the universe's baby photo, and it is the last thing light can ever show us. The unobservable universe. Beyond the CMB lies something physics strongly suggests exists but can never confirm: the rest of the universe. The region of real space that stretches beyond our observational horizon follows the same laws of physics as everything we can see. There is no reason to think it suddenly stops. In fact, measurements of the universe's geometry show it is flat to within 0.4%, and a truly flat universe is either infinite or so large the difference is meaningless. Some estimates, based on inflationary models, suggest the total universe could be at least 250 times larger than the observable portion, though this figure depends heavily on which model you use and should be treated as an order of magnitude guess rather than a measurement. The most likely truth is that out there, beyond everything we will ever observe, more galaxies are forming, more stars are burning, and more planets are spinning around, suns we will never name. It's the same story as ours, told in the dark, to no one. The last scattering surface. There is another kind of edge, not in space, but in time, and it sits even deeper in the universe's history. Before 380,000 years after the Big Bang, the universe was a dense, opaque plasma of electrons and protons, hot enough, around 3,000 Kelvin, that photons couldn't travel more than a short distance before being absorbed. Light couldn't move freely. The universe was effectively a wall of glowing fog in every direction. That moment when the plasma cooled enough for electrons to combine with protons and form neutral hydrogen, allowing light to finally travel, is called the last scattering surface. It is the absolute farthest back in time we can ever see using any form of electromagnetic radiation. Before it, a curtain, permanently closed. Gravitational waves and neutrinos theoretically carry information from even earlier, from the first fractions of a second after the Big Bang, but we currently lack the tools to read them clearly. The universe's earliest moments are sealed behind physics itself. Eternal inflation and bubble universes. Here is where things stop being astronomy and start being something closer to science fiction, except the math is real. The leading theory for why our universe looks the way it does is called inflation, proposed by Alan Guth in 1980, which suggests the universe underwent an explosive period of expansion in its earliest moments. Andre Linde later extended this into eternal inflation in 1983, which argues that this inflationary expansion never fully stopped. Instead, quantum fluctuations cause random pockets of space to stop inflating and bubble off into their own universes. Ours is one of those bubbles. Outside our bubble, space continues expanding faster than light, making it permanently unreachable. Other bubbles could be forming right now in every direction, each one potentially becoming a universe. If two bubbles collided, the impact should leave a detectable bruise on our CMB. Scientists searched for this in 2011 and found no confirmed evidence, but the search continues. The outside of our universe, in this picture, is an endless, dark ocean of inflating space with tiny lit bubbles drifting apart and never meeting. The multiverse with different laws. If bubble universes exist, there is no guarantee they all play by the same rules. In our universe, about 26 fundamental constants, numbers like the strength of gravity, the charge of an electron, and the speed of light have very specific values. Change any of them significantly, and stars can't form, atoms fall apart, or matter ceases to exist at all. Our universe appears, against enormous odds, to be fine-tuned for complexity. One explanation is that there is an enormous number of bubble universes, each with different constants, and we exist in this one simply because it's the kind that produces observers. This is Max Tegmark's Level 2 multiverse. These aren't parallel timelines where you made a different choice this morning. They are entirely separate regions of space, with fundamentally different physics, most of them dark, empty, and structurally incapable of producing anything interesting. Ours, by comparison, is almost unreasonably hospitable. The many worlds interpretation. Separate from bubble universes and operating on a completely different axis is the many worlds interpretation of quantum mechanics, proposed by Hugh Everett III in 1957 and named by Bryce DeWitt. In standard quantum mechanics, particles exist in a superposition of states until observed. The Copenhagen interpretation says the wave function collapses into one outcome. Many worlds says it never collapses. Instead, every possible outcome actually occurs, and reality branches into parallel versions at every quantum event. Every radioactive decay that could go either way, every photon hitting a detector, every quantum interaction in your neurons right now is splitting reality into branches. These branches don't exist somewhere out in space. They exist in a mathematical structure called Hilbert space, which has no physical location you could point to. You have counterparts in branches where everything went differently, from this morning back to the formation of the solar system. The unsettling part is that many worlds is not fringe physics. It is one of the most seriously debated interpretations of quantum mechanics among working physicists today. The mathematical universe. Hypothesis. Max Tegmark takes all of this one enormous step further with what he calls the mathematical universe hypothesis, outlined in his 2014 book, Our Mathematical Universe. The argument is this: our universe isn't described by mathematics the way a map describes a territory. It is mathematics. Physical existence and mathematical existence are the same thing. If that's true, then every mathematically consistent structure, every set of equations that doesn't contradict itself, exists as a real physical universe somewhere. Universes where time has 3 dimensions. Universes where cause doesn't precede effect. Universes built on geometries that have no equivalent in human experience. There is no outside to this framework because the collection of all consistent mathematical structures is, by definition, everything that can possibly exist. This is contested among physicists, and Tegmark himself acknowledges it sits at the border between physics and philosophy. But the logic is difficult to dismiss cleanly, which is why it refuses to go away. The heat-death boundary. Eventually, the question of what's on the other side of the universe merges with the question of what's at the end of time, and the answer to both is the same: nothing, slowly. The universe's expansion is accelerating, driven by dark energy, and as it does, galaxies beyond a certain distance are already receding faster than light. Over trillions of years, they will disappear beyond our horizon one by one. Stars will exhaust their fuel. Stellar remnants will cool. If protons decay, as some grand unified theories predict, they would do so in roughly 10 to the power of 34 years, dissolving the last solid matter. Black holes will survive longer, evaporating through Hawking radiation over timescales up to 10 to the power of 100 years. After that, the universe reaches maximum entropy, an infinitely large, perfectly uniform, near-zero temperature void where no gradients exist, no energy can flow, and no events can occur. Time, in any meaningful sense, stops. The heat death of the universe and the edge of the universe point toward the same horizon, the unknowable. Every item on this list, from bubble universes to branching quantum realities to infinite mathematical structures, is a theory built on inference and mathematics rather than direct observation. And there is a reason for that, which is worth saying plainly. The universe expands at roughly 70 kilometers per second per megaparsec, meaning space beyond our horizon recedes faster than any signal could ever travel. No probe, no telescope, no future technology will return information from beyond the edge. It is not a matter of better equipment. It is a matter of the universe's geometry, making the question physically unanswerable. Asking what's on the other side of the universe may be like asking what's north of the North Pole. The question sounds valid, but the coordinate system breaks down before you arrive. That's not a failure of science. That is the honest frontier, the place where human curiosity runs directly into the hard wall of what physics permits us to know, and stands there staring. If you want to see more, click the video on screen now.